Hello everyone, today I will be talking about the effects of epinephrine when it is administered into the body through medicinal uses. So this may be when someone's going through an allergic reaction or if there's another means for medicinal use. So what is epinephrine and is it related to norepinephrine? So epinephrine's background, basically it's a hormone and a neurotransmitter, so it actually has two uses basically in the body. And it's primarily produced in the adrenal medulla. Naturally, that is, unless it's injected in you, of course. And it is related to norepinephrine, but they are completely opposite things, and we'll get into that in a second. That fight or flight response that we all commonly know, epinephrine is responsible for that response. And one of its main functions that we know about is regulating heart functions and as well as dilating certain blood vessels. So now when looking at epinephrine compared to norepinephrine, we'll go into four categories: the heart, tightening blood vessels, dilating blood vessels, which is when they expand, and dilated bronchi, which is basically your lungs, right? So for epinephrine's role in the heart, it basically makes strong amplification in your heart rate. So when you have that fight or flight response or that adrenaline rush, it makes your heart rate go higher to increase blood flow throughout your body. Whereas norepinephrine, it does not do a crazy amplification to your heart rate. In fact, norepinephrine is responsible for your constant 24/7 heart rate, right? Without it, you would not be alive. It is the reason why your heart is constantly beating. And that's how the two differ, really, is because epinephrine is for those short-term bursts for the fight or flight response, for example, whereas norepinephrine is constant. And for tightening blood vessels, so the whole purpose of tightening blood vessels is to redirect blood flow to other more important areas, like other organs, right? So when epinephrine is administered or produced naturally in your body, what happens is it'll tighten the blood vessels around the soft muscles, such as your stomach, your small intestine, your large intestine, because your body's last priority in that moment of a fight or flight moment is to do digestion. You're trying to run away from that bear, right? The last thing you need to do is digest that sandwich that you ate earlier, right? So it redirects that blood flow. And then next to this is dilate blood, and it'll actually dilate the blood vessels next to your skeletal muscles. And by definition, skeletal muscles are the muscles that you can voluntarily control, such as your arms, your legs, anything of the sort. You kind of get the idea. And then for dilated bronchi, or bronchi, however you pronounce it, it opens or dilates the lungs to increase respiration to get more oxygen into your bloodstream. Because what's the point of more blood flow if you're not getting more oxygen and energy to your muscles? And then for norepinephrine, when it tightens blood vessels, it doesn't, since norepinephrine doesn't have a targeted source, right? Like it's for constant blood pressure, constant heart rate. It doesn't tighten any specific blood vessels. Instead, it just tightens all of them. Whereas for dilating blood vessels, doesn't dilate, because since it tightens all of them, it doesn't dilate any. And for expanding your lungs or your bronchi, it basically has no effect, which is one of the reasons why norepinephrine isn't used in medical emergencies such as anaphylaxis or asthma. Moving on to looking at epinephrine's relationship to the heart's functions. I already discussed previously its main focuses are increasing heart rate, increasing the systolic blood pressure, which is the pressure when your heart closes, right? Because your heart's a pump, it opens, closes, opens, closes. Systolic pressure is when it closes, right? And it does affect both, but we're going to focus on systolic pressure only instead of diastolic pressure, because I feel like systolic pressure does have a better grasp for epinephrine's function. These graphs, these are just kind of just for visual. These are linear graphs, whereas in real world scenarios, it is not linear. But I just want to show you that as you add more epinephrine, the heart rate increases, and as you add more epinephrine, the systolic pressure increases as well. All right, so now that we have that covered, we're going to be modeling the epinephrine's effect on the human heart, and this is the data that we will be using for this entire project, right? You'll notice right here that infusion rate is boxed out, but that's just because it's kind of irrelevant. It's more of the same math, which we don't need it right now. I'm just trying to explain how epinephrine directly affects the heart rate and systolic blood pressure. So This data you don't really need to know right now. We'll use it later on, but just to show you, this is the data that we will be using. And so you'll see two formulas on the bottom right here, the derivative formula and the solution formula, and we'll be using both of these formulas for both the heart rate and systolic blood pressure. We'll just replace the F value with H for heart rate and S for systolic blood pressure. And you'll see in the bottom right here, achieving a vital sign that's out of a livable range, like such as for less than 90 or over 180 for systolic blood pressure, or less than 40 beats per minute or greater than 100 beats per minute for heart rate. If the output is ever those values, it'll be set to be impossible with this solution formula. So basically, any epinephrine input that results in a vital sign that is higher than that, it'll result in the formula maxing out at that point, because anything past that is maybe not death, but definitely a dangerous scenario that we do not want to be implicating inside of a medical scenario. So I designed the formula to avoid getting below or over those limits. Okay, so now we'll be looking at the change in heart rate from the epinephrine concentration. You'll see the derivative formula that we talked about earlier and the solution formula on the top right here. And this is derived from the table that we mentioned earlier with all the data. And I'll go into what all this means, right? So the X value, basically the input, whatever you input, would be the plasma epinephrine concentration. So the first number right here, any one that you want to choose. And then HX, which is like the result of heart rate after X input, is the heart rate in beats per minute, right? And then the H max is the maximum heart rate until dangerous conditions, which is estimated to be at 100 beats per minute, which is what the value I'll be using. And then H0, which is basically in this scenario the same as H minimum, which would be the heart rate when there's zero epinephrine administered. We're going to assume that the heart rate is the lowest possible safe-ish condition, which would be 40 beats per minute, right? And then looking at the K value, it's how many beats per minute the heart rate or the heart increases for every one picogram per milliliter of epinephrine that is in the plasma, right? So you see a big number right here, 178. We're gonna find out how to get K from just 1. And then E is another constant value, which is used in all of math. It's the same exact number. It's like pi, you know how it's 3.14 or whatever. E is the same concept, kind of, just to show growth in exponential equations. And the value is about 2.718. Okay, so now we're going to move on to the actual math part. To get the solution formula, you do need to do a little bit of math with the derivative formula, but we're not going to get into that because it is a lot of calculations, and I really doubt that you're interested in that. So we're going to skip over to the math part. And if you just want to take a second and pause the video, this is all the outputs. And if you check, this is the K value, 0.0784, and that is for heart rate. It'll be different for systolic blood pressure, but for heart rate, for every 1 picogram of milliliter of epinephrine that is in the blood or administered in the blood artificially, it'll increase the heart rate by 0.078. And if you actually check the final values, you'll see that when I put a value of 178 from the X value right here, it eventually does give 47.82, which is very, very close to the actual result from the study of 48. And the same goes for this value right here, which did end up at 51.03, and the actual value was 52. And the next one, it was 57, and I got 58.9. It is a little off, but it's very hard to get it exactly right with a simple formula like this. But just to give you an idea, on what would happen. And if you administered a bunch of epinephrine, it would equal 100 maximum, because I set it to equal a maximum of 100 because we don't want the heart rate ever exceeding over 100. And if you put 0, you'll see that the value is 40. And let's say we'll do our own value. Let's say the X value is 800. So it's neither of these values is our own value. It said that the heart rate would be 67.97. All right, that's it for the heart rate. We're going to move on to systolic blood pressure now. As you can see, we have a new set of Y values. The X values are the same because when they administered in the test those amounts of epinephrine, they got blood pressure results and heart rate results from the same patients. So this is what we got on average. And this is right here what the expected systolic blood pressure was going to be, or not expected, that is the actual results from the test that they did. And then if we look at the values right here, the X value is the same as the heart rate. It's just the plasma epinephrine concentration in the blood, which is 1 picogram for every 1 milliliter of blood, or plasma, sorry. plasma is the liquid part of your blood. And then S of X is the systolic blood pressure measured in millimeters of mercury, so mmHg. And then for S of max, which is basically the maximum systolic blood pressure until dangerous conditions, which is estimated to be around 180 millimeters of mercury. It's the same concept as the heart rate, right? Anything over that is dangerous. And for the S0 or the S minimum, X equals 0, so 0 extra plasma epinephrine concentration. The absolute minimum rate would be 90 millimeters of mercury for the systolic blood pressure. So that's the pressure for when the heart closes, right? And that's basically what gets our blood moving. So if that's lower than 90, our blood isn't going to be moving through our body efficiently, and we're going to start lacking those nutrients, oxygen, and just everything that our body needs to keep living and thriving. And then for K, it's the same thing. It's going to be a constant for one X value or one plasma epinephrine concentration for 1 picogram for every 1 milliliter. So instead of 178, if we say 1, that X value for this one is 0.1333, right? So it is different than the heart rate, as you can see, because they're completely different vital signs. So why would they have similar K values, right? And then E, same thing. It's just a regular constant. So as you can see, the formulas are the same. If you check, I just replaced H with S. And then I didn't explain it in the heart rate originally because I wanted to explain it in systolic blood pressure. So how this works is you take the S max, which would be the 180, and then you're basically taking that and adding it to this collected parentheses for the minimum minus the maximum. And then you're going to multiply that by E to get the growth factor, and then the E to the exponent value, which is the constant K times the X value, which for this scenario, let's say we're going to do 178. So K, which is 0.1333 times 178, divided by S maximum, which we discussed is 180. And we make that negative, that'll be the exponent value of E. And if we solve that, eventually we saw that we got 101.11. So it was pretty close to the actual result, which was 98, and it was only 3 off, right? So not bad at all. And then we'll go to check the other ones, and the other values seem to be really close too. And so that's kind of it for the systolic blood pressure and the heart rate. As you can see, it's a pretty basic formula, but it can be very, very useful for estimating how much epinephrine a patient does need in a medical setting, especially in a medical emergency. And so that basically covers it for my project. Together we went over the heart's response to epinephrine using calculus through derivative and solution formulas. And we also covered how higher doses of epinephrine do lead to higher heart rates, systolic blood pressure, diastolic blood pressure, and it can even tighten or dilate certain blood vessels in the body. And I think we can all agree that, especially in medical emergencies, epinephrine is critical in emergencies. So that pretty much covers it. And thank you guys for watching my presentation. Here's all my credits and sources. I hope you guys have a good one. Thank you.